Okay, so in this video, we're going to be looking at how to solve a vibrating masses problem. Um, this will likely be a question on the final exam. So it's definitely important that you know how to do it before the final. This problem is taken directly from the assignments. And so part A asks to find the normal frequencies of vibration. Which in this case, since it's only a two mass system, are going to be omega 1 and omega 2. As you can see, there's three springs attached to masses. The masses have displacement of x1, x2. So to find the normal frequencies of vibration, we're going to use the Euler-Lagrange equation. So which looks like this. d by dt of partial L partial q dot minus partial L by partial q is equal to 0. Q are the positional variables which we'll be using in our problem. So this is the general form. We can express, so we need to clearly find what L is, which is Lagrangian. We can express Lagrangian as L is equal to T minus V, so the difference between the kinetic potential energy of the system okay, so to find L, we need to find T and V. So for the kinetic energy, which is T, the whole system, mass 1, so T1 is equal is going to be half mv squared, right? So it's going to be half m1 x1 dot squared. Since m1 is 1, that's just going to be equal to half x1 dot squared. And then for mass 2, T2 is equal to half 2 x2 dot squared. And since m2 is 2, that's just going to be equal to x2 dot squared. So T is going to be half x1 dot squared plus x2 dot squared. Now for V, which obviously deals with the springs, because you have the formula for V is half k x squared. So for spring 1, V1 is equal to half k1 x1 squared. So the displacement of mass 1 represents the displacement of the same string, or the same spring, I should say, because the spring is attached to the wall. So if m1 moves the distance x1, that will be the compression or extension of that spring k1. So that's why we express that potential energy. For spring 2, the compression or extension of spring 2 will be governed by both the motion of mass 2 and mass 1. So V2, I should say V1, 2, because between the two masses, it's going to be half k1, 2 x2 minus x1 squared. You can rewrite the first expression, since we know k1 is just 1, that's going to be half x1 squared. And the second expression is going to be x2 minus x1 squared. Spring 3 will just be V2 is equal to half, right? It's equal to half k 2 x2 squared. That's equal to x2 squared, since k2 is just 2. So you can write V as half x1 squared plus x2 minus x1 squared plus x2 squared. And expanding this further to simplify our work later, we can expand the middle part. That's just going to be equal to 3 over 2 x1 squared minus 2x1 x2 plus 2x2 squared. So the Lagrangian L is equal to t minus v, and that's just going to be equal to half. So sorry, writing out t minus v, we're going to have half x1 dot squared plus x2 dot squared minus 3 over 2 x1 squared plus 2 x1 x2 negative 2 x2 squared. Now applying the Euler-Lagrange equation, which is highlighted here, we're going to take the partial derivative of L with respect to both x1 dot and x2 dots to replace the q, and then we're going to also take the partial derivative of L with respect to x1 and x2 to replace just the q on the right side there. So we're going to use that equation basically. So first, we're going to solve in terms of for x1. So partial L by partial x1 dot. The equation is going to look like this. The total equations are going to look like this. Sorry. L by partial x1 is equal to 0, and d by dt partial L by partial x2 dot minus partial L by partial x2 is equal to 0. So we're going to have to solve these two equations basically, not just replacing x1, x2, which are positional variables, with the q in the general equation. So first we'll solve partial L by partial x1 dot. That's going to be equal to x1 dot. And then d by dt of x1 dot is just x1 double dot. Partial L by partial x1 is equal to, it's going to be equal to negative 3x1 plus 2x2. So putting these into the equation above, we're going to have x1 double dot plus 3x1 negative 2x2 is equal to 0. That's equation 1. And then similarly for x2, d by dt, sorry, partial L by partial x2 dot is equal to 2x2 dot. And then d by dt of 2x2 dot is equal to 2x2 double dot. And partial L by partial x2 is equal to negative 4x2 plus 2x1. So putting these together, we're going to have 2x2 double dots plus 4x2 minus 2x1 is equal to 0. So that's our equation 2. Okay. So we can rewrite these two equations in matrix form, which is the next step in order to find our normal modes of vibration, or normal frequencies of vibration, I should say. So we've write these in matrix form. We can rewrite this as the coefficients of both the double derivative terms. So the matrix is going to be as follows. Then we're going to add the coefficients of the x1 and x2 terms. So be very careful in this step, especially to ensure that your matrix yields the same result as your equations of motion. So in our case, our matrix is going to look like this. We can check here if we multiply the two numbers that relate to the variable x1 or 3 here and negative 2 here. And as you can see, if you look at our equations, those are the coefficients of x1, both the equations, so you know we're good. And likewise with x2. And that's going to be equal to just 0 vector. Okay, and now this is in the form bx double dot plus ax equal to 0, where B is a matrix. For the quadratic form of T, the kinetic energy, and matrix A for the quadratic form of the potential energy V. So the solution in general, the solution we've seen in ODEs, the solution to the ODE of the form bx dot plus ax equal to 0, where b and a are just numerical constants, not matrices, is x of t is equal to c1, which c1 is some constant, cos k is a constant t. In our case, we have matrices. We have matrices, so we let the solution be x of t is equal to y cos omega t, where omega is what we're looking for. That's the natural frequency of our system. And where y is a constant vector. So as you can see, we have an x in this form here. This form here. We need to find what x double dot is so we can substitute. So x double dot is going to be negative omega squared y cos omega t. And if we sub into our equation, bx double dot plus ax is equal to 0, we're going to get as follows. Cos's cancel. We can simply rewrite this as a minus omega squared b y is equal to 0. This is called the modified eigenvalue equation. You should always reach this step when solving the vibrating masses problem. Now, this is a system of two homologous linear equations, since we have, well, as you can see above, we had two homologous linear equations for two masses. And the solutions are in y1 and y2. So for a non-trivial solution, we'll want the determinant, these are the y's, we'll have the determinant of this part equal to 0, which is the only way we can have non-trivial solutions for this problem. So determinant of a minus omega squared b is equal to 0. So let's solve this. I will do for the first one only. So a minus omega squared b. So if we look here, this is our a, this is b. So a 3 minus omega squared b. So we're going to have 3 minus omega squared times 1, the first spot, which is going to be 3 minus omega squared. And then for the diagonals, we're going to have negative 2 minus 0 because omega squared times 0 is 0. And then for the bottom right, we're going to have 4 minus omega squared times 2. So it's going to be the determinant of this matrix. And just calculating the determinant, that's going to be equal to 3 minus omega squared times 4 minus 2 omega squared minus 4. That's 0. And if we expand this, we're going to get 12 minus 6 omega squared minus 4 omega squared plus 2 omega 4 is 4. That's equal to 12 minus 10 omega squared 2 omega 4. I'm going to actually simplify. 12 minus 4 is obviously 8. So it's going to be negative 10 omega, it's going to be negative 10 omega squared plus 2 omega 4 plus 8. Dividing through by 2, it's going to be omega 4 negative 5 omega squared plus 4 is equal to 0. Now we can see that that simply simplifies to omega squared minus 1 omega squared minus 4. And from here, we can just solve for our omegas, which are omega 1 and omega 2, which are the natural frequencies of the system, which is our solution to part A of this problem. So, sorry, let me zoom out. So, omega is equal to 1. This gives omega is equal to 2. Omega 1, omega 2. You'll want your natural frequencies to be positive, obviously, so you force them to be positive, don't take negatives. This is always going to be the case. Alternatively, we can just go from this step here and guess omega if it's not an easy simplification, if it's not an obvious factor. Here, if we can just guess omega is equal to 1, you'll yield the right answer. If you guess omega is equal to 2, you'll yield the right answer. In general, on an exam, the solutions are going to be low numbers. So 1, 2, 3, 4. It shouldn't be too complicated. Maybe half potentially, or 3/4. But they should generally be pretty easy solutions, or an easy polynomial to factor. So these are the natural frequencies of vibration. Omega 1 is equal to 1. Omega 2 is equal to 2. Which are the frequencies at which the masses vibrate, subject to the initial displacements. That's part A done. Part B of the problem asks to find the normal modes of vibration. So now at this stage, we're going to go back and use the modified eigenvalue equation. So it's A minus omega squared B, y is equal to 0. But we have our omega 1, omega 2 now. So we have A minus omega 1 squared B, y to the power 1. So I'll call it, it's just it'll just be to differentiate between the two solutions that we get. So this one's just going to be called y to the power 1. That's going to be equal to, so this is A minus omega 1 squared B is matrix, where we can rewrite this matrix, except for we know what omega is now. So for omega 1, for the first one, for example, we're going to have 3 minus 1 squared times 1, which is just going to be equal to negative 1. Or sorry, that's just going to be equal to 2. So I'll write this out fully. Negative 2, it's just going to be negative 0 again. And this one's going to be 4 minus 1 squared times 2. And now this time we're going to have multiplied by y1, power 1, and y2, or y2. That's just, the powers are again just distinguished between our two solutions. So it's y1 and y2. That's going to be equal to 0 vector again. Simplifying this matrix, we're going to get 2, negative 2, negative 2, and 2. y1, y2. And And then we can expand this into a system of equations. We're going to get 2y1 minus 2y2 is equal to 0, and negative 2y1 plus 2y2. And from the first, we only need to use the first equation because the equations are redundant in this case. From this equation here, we see that y1 prime is equal to y2 prime, or just power 1. And we'll say that that's going to be equal to C1. So we'll say C1 is equal to Y2 and Y1. It doesn't really matter in this case. There'll be more clarity on this in a second. So that's going to be equal to some constant C1. This allows us to write our solution for the first mode because we're using the omega 1. So the solution for the first mode is going to be y1 is equal to C1 1, 1. And the reason for this, again, why we chose C1 above, is because obviously, if you have y1 is equal to y2 is equal to c1, then this equation here is going to yield the exact same thing as above. We can write our final solution as x prime t is equal to c1 y1 cos omega 1 t. Since omega 1 is simply just equal to 1, that's going to be equal to cos t. So that's x to the power 1 t. That's the solution for this, for the first mode. Now we do the same thing for the second mode, which is a little bit more complicated, but we'll write it out now. So for second mode, a minus omega 2 squared b. It's going to be y to the power 2 this time, just to differentiate again. And then this time, our omega is equal to 2, so it's going to be 2 squared times 1, negative 2, negative 0 again. And then here we're going to have 4, negative 2 squared is 2. And here, again, we have our y's. And that's going to be equal to this matrix. And writing a system of equations again, we're going to have negative y1 squared, negative 2y2 squared is equal to 0, negative 2y1 squared, negative 4y2 squared is equal to 0. Again, these equations are redundant. We can only look at the first equation. This equation will yield y1 2 is equal to 2y2 to the power 2. Sorry, negative 2y2 to the power 2. And we'll say y2 is equal to c2. So we're going to say that's equal to negative 2 c2. This allows us to write our y squared. I think I might have, sorry, this should just say y. Y squared in this case is equal to c2 negative 2, 1. Now, if we look at this to make sure our answer is right, for the y1 case, we're going to have y1 is equal to negative 2 c2 just by looking at this here. We're going to, for the y1, which is the upper row, we're going to have y1 is equal to negative 2 c2, which is exactly what we had defined here. And we're going to have y2 is equal to c2, which is exactly what we defined here. Alternatively, for the right solution to this problem, you could say at this step, you could say that y2 is equal to negative half y1 squared, and that's equal to negative half c2. And then you can write your vector, your solution as follows. And this would yield the exact same answer, and that's completely fine. Either or work as correct solutions. Okay, and then we can write our solution again in full form. Omega 2 is equal to 2, so this is going to be our second solution. Okay, and our normal modes are simply the vectors, or simply the y's. So our normal modes of vibration are simply (1, 1) and (-2, 1). And what do the normal modes of vibration represent? They represent the relative amplitude of vibration of the masses when they're set into vibration or vibrating motion at the two normal frequencies, basically. So these are normal modes of vibration, which represent the relative amplitudes of vibration. If you want to find the total amplitude of vibration, or the absolute, you have to find what the constants C1 and C2 are, which depend on the initial displacements, as we'll find out in a second. So part C of this problem then is given the initial displacement. So if the system x naught is 1, 7, oops, sorry. And displacement, that's the initial displacement, and initial velocity to 8, determine motion. Okay, so the total motion of the system can be found as follows. There it out. So above in part B, to find the normal modes, we only considered the cosine part of the total solution. But as I said above here, here the actual total solution is C1 cos kt plus C2 sine kt. A little mistake there. In the first case here, we only consider the cos part because we want to find just the normal modes. But when we are given initial displacements, we have to consider both the cos and the sine. And these kind of vibrating mass problems, it will yield the exact same normal modes. So it's relevant to do everything a second time. The only thing that changes, if you compare x1, x2, x3, and x4, the only thing that changes are obviously the constants C1, C2, C3, C4, and also that we have cos in x1, x2, and sine in x3 and x4. By the principle of superposition, we're able to write that the total displacement xt is equal to x1 plus x2 plus x3 plus x4. Writing that out properly, we're going to get C1, 1, 1 cos t plus C2, 2, 1 sine, cos 2t plus C3, 1, 1 sine t plus C4, 2, 1 sine 2t. we apply the initial displacement. So we're going to get 1, 7, x naught obviously is when t is equal to 0. So all the sign terms disappear. That's just going to be equal to C1, 1, 1. And we solve this, expand it into a system of equations by just using the first row and the second row. So we're just going to have 1 is equal to C1 times 1 minus 2 times C2. And then we're going to have 7 is equal to C1 plus C2. And solving, this yields C1 is equal to 5, C2 is equal to 2. In the same way, we apply the initial velocity, which is x naught dot. If we take the derivative of x of t here, you'll see that obviously the C1 and C2 terms disappear, and we're going to be left with just cosines again when time is equal to 0, and we're going to be left with C3 and C4 to solve for. Be aware that a 2 will come out here because when we take the derivative, a 2 will come out on the last term here. So when we apply x naught dot, we're going to get this vector here is equal to C3, 1, 1 plus 2 C4, negative 2, 1. And again, solving system equations that we get from this. We're going to get that C3 is equal to 6 and C4 is equal to 1. So now we have our final solution. Our final solution can be obtained by plugging C1, C2, C3, C4 back into here. And we want to actually express it as the individual displacements. So we'll just take the first row and the second row and express it as x1 of t. That's going to be just the first row. It's going to be 5 cos t minus 4 cos 2t plus 6 sine t minus 2. Zoom in bits, right? Minus 2 sine 2t. Then x2 of t is the second row from the red underlined above. That's just going to be 5 cos t plus 2 cos 2t plus 6 sine t plus sine 2t. And those are our solutions for the motion of the system. So this problem is probably going to be on a final exam expressed in an extremely similar way to what I've done here. You could have another additional mass, which would yield an additional 2 springs, which would make the solution a little bit longer, would make the matrix bigger. But it can still be solved in the exact same way that we've solved here. It would just mean you have a 3x3 matrix, then a 2x2 matrix at this step here. But yes, it can be solved in the exact same way. You also see that this is very analogous to the circuit problems that you'll have in the course pack and also in the assignments. Circuit problems, there are a little bit of a few tricks at the beginning that you need to know how to work with, but then you end up getting the same equation of this form highlighted here. And you can proceed and solve in the exact same way.